Hi, I'm here to teach you a little bit about ionic bonding. We're going to start off by using what's called a Lewis dot diagram because that's the easiest way to get a sense of how to do ionic bonding. And then once you understand how the elements combine together to form compounds and all this good stuff, we don't need to do the Lewis dots anymore. So let's start with identifying the symbols, the protons, the number of electrons. Let's look at the valence electrons, and let's figure out the charge, or what is also called the oxidation state, on these following elements. If we look at our trusty periodic table, we see that potassium has an atomic number of 19. So that's going to be the number of protons, the number of electrons. Okay. Well, also by looking at potassium, we know that it is a 4s1 if we did an electronic configuration. So by doing electronic configuration, we understand that it only has one valence electron, so its oxidation state is +1. Now this +1 means that potassium wants to give up its one valence electron, because it is easier for potassium to give up that 1 than it is to gain 7 to get to 8. Remember the octet rule, they all have to get to 8 valence electrons. So I'm going to quickly fill in all of these for these following elements because there's a lot of repetition and you get the same information the same way. So protons, again, is the atomic number. Protons and electrons in this instance are going to be the same. The valence electrons come from either the group number that it's in, if you know how to do that, or you can do the electron configuration and also figure out the valence electrons. So sodium is 11. It has one valence electron, so its charge is +1. Calcium is 20 electrons, 2 valence electrons because it's in the alkali metals, so its charge is a +2, or oxidation state. So aluminum has 13 protons, 13 electrons. It has 3 valence electrons, so it wants to give up those 3, so it's a +3. It wants to lose them. It wants to give them up and become more positive. Magnesium is 12, so it has 12. It has 2 valence electrons, so it's a +2. Oxygen is an 8, so it has 8 electrons. It has 6 valence electrons. Now since it has 6 and they're trying to get to 8, it's easier for oxygen to take on 2, to gain 2 negative charges, than it is to give away 6. So its oxidation state, or its charge, is a -2. So nonmetals are typically going to be a negative. Your metals are typically going to be a positive when you're talking about ionic bonding. So then chlorine has 17, 17, 7, so it's a -1. Nitrogen is 7, 7. It has 5 valence electrons, so it's a -3. Fluorine is 9, 9, 7, -1. Iodine is 53 protons, 53 electrons. It's going to be in group 17, so all you have to do is subtract 10 from that group 17 number to get your valence electrons, or you can just count the S's and P's as well to get that. So it's going to have 7 valence electrons. It's going to be a -1. So now we know this. Let's apply this to the dots, and let's look at the transfer of electrons, because that's ideally what ionic bonding is. It's just a transfer of electrons from a positively charged element or a positively charged ion to a negatively charged ion to create a balanced or equal charge, a net charge of 0 essentially. So let's flip this over. And so I've got some examples here. Okay, we've got magnesium plus, let's let that focus, magnesium plus iodine. So if we were going to do Lewis dots for magnesium, we would do Mg. It has 2 dots because it is in the alkali metals. Magnesium's right here. Magnesium's right here, so he has 2 valence electrons, so we're going to do a dot on the top, a dot on the bottom, plus iodine. Well, we find iodine. Iodine is right here. It's in group 17. It is a halogen, so all of the halogens have Hang on, let me see if I can fix this slide. All of the halogens have 7 valence electrons. So we're going to do, remember Lewis dot, we start at the top, we go clockwise until we run out. So iodine has 7 valence electrons. Okay, so we got magnesium that has 2, iodine that gets 7. So iodine wants to get one of these from this magnesium. So we're going to draw an arrow to right there. Okay, so that iodine is now going to be 1 minus, because it gained 1 negative electron. So then what do we have to do with this other magnesium? Because this magnesium still has 1. So what we have to do is we have to add another iodine with 7. We have to draw another arrow going to fill in right there. So now our chemical formula is simply Mg I2, because we have 2 iodines and we have 1 magnesium to create that. See how that works? So these positive ions, or these cations that have only 1 or 2 or maybe 3 valence electrons, they want to get rid of those valence electrons so they can get to 8. And it's easier for them to give them to a like a halogen or oxygen or a nitrogen, because those elements can absorb those electrons very, very easily to get to 8. So let's look at the next one. We've got sodium plus oxygen. So we find sodium. Sodium's right here. It's in the first group, so it's going to have 1 valence electron. So we're just going to put it right there on the side. I know they're supposed to go on the top, but I know what's going to happen, so I'm just going to put it on the side. So we're going to do it plus an oxygen. Oxygen's right here. It's in group 16, so we take that number, we subtract 10. Because remember, we don't count the valence electrons for the transition metals because they can change depending on what they're bonded to. So then oxygen is going to have 1, 2, 3, 4, 5, and 6. Okay? So we're going to do the same thing we did on this top one. So we got to add this Na. This Na wants to give up its lone electron, and it wants to move it right there. Okay? Well, now oxygen is still not happy because it doesn't have 8. Remember, they want to get to 8, the octet rule. So we have to add another sodium. With the dot, we got to draw the arrow the same way, and we're going to transfer the dot. So now our formula works as this. We've got 2 Nas, and we have 1 oxygen. So we do Na, 2 oxygen. So that's just sodium oxide. Okay, let's do one more Lewis dot, and then we'll do it a different way that I call the swap and drop. So sodium, okay, we just did sodium. So sodium has 1 valence electron plus chlorine. Chlorine's right here. It's a halogen. It's in group 17, so we're going to take 10 from that number. So it's got 1, 2, 3, 4, 5, 6, 7. Okay, it's almost happy, but it's not quite happy. So it's going to say this sodium, hey, I need your electron. He's going to say, all right, you got it. So now we have 1 Na, 1 Cl. So we do NaCl, and we simply have sodium chloride or table salt. So let's do the last two a little bit simpler way. It's going to be called the swap and drop method. So we got calcium and fluoride, or fluorine. It's going to make calcium fluoride. So if we look on the periodic table, calcium is the alkali metal. It's in group 2, so that means it's going to have 2 valence electrons. So we're going to do Ca, 1, 2. So we're going to do that. Okay, and then we're going to do fluorine, which we know has 7. So we're going to do that. We're not going to draw the arrows on this one. We're going to do what's called a swap and drop. So Ca, we said, is a 2 positive because it wants to give up its 2. Fluorine is a 1 minus because it wants to give up, or it wants to gain 1 negatively charged electron. So it's needing to get more minus. So now what we do is we swap the numbers and the symbols go away, and that gives us our formula without doing the dot structure. So we're going to take this 2 and we're going to put it with the fluorine. We're going to take the 1 and we're going to put it with the calcium. So that means our formula would be Ca1, which we don't write the 1 because we already have 1 there. And we're going to take this 2 that's with this fluorine. That just means we have to have 2 of those. So we're going to put a 2 down low. So the swap, and then you drop the charge. And we could draw this out too, so we would need 2 fluorines to absorb both of those valence electrons. So they'll swap and drop. So aluminum, and then we got chlorine. Okay, aluminum's right here. It is in the boron group, so that means it's simply going to have 3 valence electrons. Again, we take this top number, which is 13, and we're going to subtract 10 from it. So it's a positive 3. Chlorine and fluorine are in the same group. They're both halogens. They have 7 valence electrons, so they want to become negatively charged by 1 electron. They want to gain that 1 so that they have 8. So it's going to be a minus 1. So we're going to do the same thing up here. We're going to circle the number or the charge, and we're going to switch it. We're going to swap it with the other element, and we're going to drop the charge, and we're going to put it down low. So that means we're going to have 1 Al for every 3 chlorines to get that, because the net charge of these has to be a 0. Net charge needs to be 0. If the net charge isn't a 0, they're not going to bond together because they want a net 0 charge of 0, at least in ionic bonding. Covalent bonding is a little bit different because it's the sharing of valence electrons. Well, this is the transfer, so they want them to be the same. So that's it for today. If you need any other help, please let me know.